Thin film interference. There's another interesting effect caused by light's properties of refraction, reflection, and interference. It occurs when you have light passing through multiple media with different indices of refraction. Light first passes through a thin film. A thin film is a media layer with a thickness that ranges from 10 to the negative ninth meters to 10 to the negative 6 meters. Depending on the structure and materials of the media, the refracted light interferes with the partially reflected light to produce maxima and minima. The minima are where little to no reflection is seen, and the maxima are where wonderful colors and unique patterns are shown. Lens coatings are an example of destructive interference and are designed to reduce reflected glare. The glasses on the top do not have an anti-glare coating or thin film, and the reflection of the person standing above the glasses is seen. With the anti-glare coating, the light is transmitted mostly through the lens, and there's much less reflection, shown here. This helps make photographs of people with glasses look better, and enables you to see the person's eyes behind the glasses. The behavior of light reflection and transmission is similar to the behavior of mechanical waves on a string. When a light wave or a mechanical wave encounters a boundary, part of the wave is reflected and part of the wave is transmitted. This is easier to see if the mechanical wave transmitted through a string is examined. Here we have two different scenarios. We have a light segment of string into a heavier segment of string. And here we have a heavy segment of string moving, and then it bumps into a light segment. So the transmitted pulse is upright, regardless of whether the new material is more dense or less dense. So let's say we had a person here, and this is their hand, and they shake the string that way so that it sends this pulse down. A pulse that remains upright after the reflection here, or after the transmission, is said to experience a zero phase shift. So we have light string, it bumps into the heavy segment. The light segment is going to have a partially reflected pulse on the bottom side of the string, and part of that original wave is going to be transmitted through in the same direction, and it's going to be above the string like it started out. If you start with a more dense material and you go to less dense, then the reflected portion and the transmitted portion will both still be upright. The reflected pulse inverts when it encounters a denser medium, like in the first case. See how it flipped over from the top side to the bottom side. However, if the new medium is less dense, the reflected pulse will stay upright after it reflects there. See that? A pulse that inverts, like this one, is said to experience a 180 degrees phase shift, also known as a phase shift of lambda over 2. We'll use the same principles as we consider two cases of the transmission of light, a film coating and a bubble. Consider a ray of light incident on a thin film over a second layer of greater index of refraction, in this case, glass. So this is the anti-glare example. The values of n increase with each layer. So light is moving really fast, then it moves a little slower, and then it moves even slower. The portion of the wave that passes into the film layer remains in phase. There's no phase shift for the transmitted wave. The portion of the wave that reflects off the film layer is phase shifted by lambda over 2 because the film has a higher index of refraction than air. The reflected wave phase shift is analogous to a pulse moving from a less dense to a more dense medium. This whole thing happens again once the transmitted light hits the second interface. Because this is denser, the glass is denser than the film layer, the same thing happens where the reflected portion of light is also shifted by lambda over 2, and the transmitted wave is not phase shifted. Although for our purposes, we're not even going to care about any of this portion of the light that continues on through the glasses. We're only concerned with this reflected ray and this reflected ray. The ray reflected off the glass layer here is finally transmitted back into the air. There's no additional phase shift here because we're just transmitting it through. But the lambda over 2 shift from the glass layer remains. The ray originally reflected here and the ray reflected from the glass here are both in phase because they both were phase shifted the same amount. If the thickness of the film layer is T, then that means the extra distance traveled by this second ray, the red ray, is about 2T, or, at a minimum. Although on the AP Physics 2 test, I've only ever seen thin film interference problems where the incident light ray is going straight in so that they've removed the angle of incidence, so that you only have to think about the extra distance traveled as being 2T. If this extra distance, if 2T equals some sort of integer number of wavelengths, then that's going to mean that these waves are still in phase with each other and there will be constructive interference. However, if that extra distance traveled by the second wave is 1.5 wavelengths or 3.5 wavelengths, then destructive interference will occur. Important, the extra distance traveled occurs in the film. So what's going to be important is the wavelength of the light in the film. The wavelength of the light out here makes no difference to what's going on inside the film and whether or not these two rays are going to still be in phase with each other. You really do only care about what's going on inside the film, what is the wavelength here, and how much extra distance has that second wave gone through. Okay, so if the transmitted ray here travels an extra distance of exactly 2T, so we're assuming actually that the light's going straight in, it's not actually going in at an angle like this. If it's going straight in, that transmitted ray is going to travel exactly 2T extra distance. If that is an integer multiple of the wavelength of the light inside the film, then these two waves at the end will be in sync with each other. See how the troughs line up with the troughs, the crests line up with the crests, and you will get constructive interference if your eyeball's over here and you're looking at the light hitting your eye. These will be in phase with each other. However, if 2T, this distance here, the extra distance traveled, is half a wavelength off, then these waves will no longer be in sync and there will be destructive interference. The second type of thin film interference is similar to a soap bubble, where there's air above and below the thin film of soap. In the second case, we have a ray of light incident on a thin film, which is over a second layer of lower index of refraction. So light moves fast, then slower, then fast again. The first part of this analysis is the same as before. The incoming light hits the slower medium, some of it bounces back, it reflects, and it shifts by lambda over 2, and the transmitted wave goes through but has no phase shift. However, what happens next is different. Because the light is bouncing off an interface that's less dense, we're going to have a reflection here, but there's not going to be a phase shift the way there was before. And once again, there's transmitted wave that also goes through with no phase shift, but we don't care about that for our purposes, right? Our eyeball is over here looking at this light, and it's seeing this ray, and it's seeing this ray. So we're going to see what happens now that this ray does not have a phase shift, since it's bouncing off a faster medium. The ray reflected off the bottom of the soap layer is finally transmitted back into the air. But again, there is no phase shift because this reflected ray bounced off of a faster medium, and there's never a phase shift when you're transmitting straight through. The ray reflected off the top of the soap, here in blue, and the ray reflected from the bottom of the soap and transmitted out of the soap are now out of phase because this one was phase shifted and this one wasn't. Again, if the thickness of the soap layer is T, then the extra distance traveled by the second ray is a minimum of 2T. It would be exactly 2T if the light goes straight in and then bounces straight back. That would be 2T since that distance is T. If we neglect the fact that this is coming in at an angle, we can assume it's just 2t is the extra distance. If this extra distance is an integer multiple number of wavelengths, then destructive interference will occur because one of those is phase shifted and the other isn't. So they'll remain out of phase if the amount of extra distance here is an integer multiple of a wavelength. However, if this extra distance is an odd multiple of half wavelengths, then the waves will be shifted back into phase and constructive interference will occur. In conclusion, for case 2, where we go from fast to slow to fast, these are going to be out of phase. So this extra distance, if you want there to be constructive interference, you're going to have to get them back into phase by being 1.5 wavelengths or 3/2 wavelengths, so that since they're already out of phase, you need to get them back into phase by using this condition. So this was the equation for destructive interference in case 1, but here they're switched. So here, if you want destructive interference, then you want that extra distance to be exactly an integer multiple of a wavelength. It's interesting to note that the equations for case 1 and case 2 are swapped for constructive and destructive interference. And this is because of the different pattern in the indices of refraction for each case. So here we have a low index of refraction to medium to high. Here we go low to high to low. So the light moves fast, then slower, then slowest. And here we're going fast, slow, fast. Light with a wavelength of 560 nanometers, so the wavelength in air is 560 times 10 to the negative 9th meters, illuminates a soap film with an index of refraction of 1.4. What is the minimum thickness of the soap film in order to produce no reflection? So we want destructive interference. All right, let's examine this on the next slide. We are going to use this equation, but let's draw a picture and reason through why. So the soap film is going to have, we're going to have air, then soap, then air again. So the light's going to come in and it's going to travel 2t, so this is t. It's going to travel an extra distance of 2t, and there will be a phase shift between these two. So lambda over 2, I'll write that to be the phase shift. So we want destructive interference, which means they're out of phase right now, and we want them to stay that way. So that's why we need this extra distance traveled to be exactly equal to a multiple integer of a wavelength. When they say the minimum thickness, that would be what is the smallest thickness. So that would give us an m of 1, right? We don't want to have this m value be greater, right? 1 wavelength would be the shortest extra distance that you could travel where we would get that destructive interference. So we want 2t to be equal to exactly 1 wavelength. So therefore the t, the thickness, would have to be wavelength over 2. Now we did that here. We want to find the wavelength in the film. So remember, they gave us the wavelength of the light in air, but that does not matter. What really matters is what's happening inside this film. We need to make sure there's 1 full wavelength in the film. So what we care about is the wavelength of the light in the film. So we have the index of refraction of the material, so we can then calculate the wavelength of the light in the film, which is 400 nanometers. This is now continued on the next slide. All right, so when the light hits that interface, it's going to move slower. So it's actually going to decrease that wavelength. Remember, lambda equals v over f. This is on the AP Physics 2 equation sheet. The frequency of light is not going to change when it goes through different mediums. So if the velocity decreases, the wavelength of the light decreases. So we now know that the wavelength of the light inside the film is 400 nanometers. And you can use your definition of index of refraction in order to come to that conclusion on the previous slide of how to convert to find the wavelength in the film. All right, so now we're back to this equation. We know that m is going to be 1 because we want the minimum thickness of the film. So t has to be 1/2 of the wavelength in the film, which gives us a minimum thickness of 200 nanometers. So remember, the minimum thickness is found by setting m equal to 1. If m was 0, there would be no soap bubble. M1 is going to be the thinnest possible soap layer. If m was 2, then we're going to have exactly one wavelength all the way through. Well, one wavelength would be lambda over 2. So lambda over 2 plus lambda over 2 gives you one full wavelength. But if we had an m value of 2 in here, then we're going to have a thickness of the full wavelength. So one full wavelength down to one full wavelength back would give us 2 times the wavelength would be the extra distance traveled, which is why we're going to use m is 1. That's going to give us the minimum thickness. The wavelength can be left in nanometers, as the thickness of the soap bubble can be measured in nanometers. Light with a wavelength of 650 nanometers illuminates the lenses in a pair of glasses with a thin anti-glare coating. The coating has an index of refraction of 1.3, and the glass has an index of refraction of 1.52. What is the minimum thickness of the coating that will provide for maximum transmission and minimum reflection? Since we don't want any reflection, we want destructive interference. So if we have case 1, where we have the light coming in into slower medium and then bouncing off an even slower medium, we're going to have the phase shift in this ray. We're also going to have the phase shift from this ray. So in order to get them out of phase, we need m plus 1/2 in here so that they will then shift and lead to no reflection. So that's why we use this version. We're going to solve this for t, and then we're just going to, first we have to find the wavelength of the light in the film, because that's going to make a difference for if you have your full wavelength in here or not. The wavelength in the film is what's important, not the wavelength in the air. So first, we're going to convert and find that wavelength in the film. All right, so n is given for the glass block, but we don't need it in the equation. It's only used to determine which equation to use. Since n of the glass block is greater than n of the coating, we were in case 1. So that's how we figure out which equation to use. Then we're going to substitute in our givens, and we find that the minimum thickness would be when m is 0, because we have this 1/2 in here. So we get 125 nanometers. Because we have a 1/2 in here, we can make this 0 safely, like the minimum value that we can possibly put in here, and still have an equation. We can actually put 0 in here, whereas before we had to include a 1. Light with a wavelength of 660 nanometers illuminates a soap bubble with an index of refraction of 1.2. What is the minimum thickness of soap in order to produce maximum reflected light? So this is case 2. The light is coming in, it's going slower, but then it's bouncing off of air again. So we're going to have a phase shift here. But are we going to have a phase shift here? No, we are not, because we're bouncing off a faster medium. So we do not get the phase shift, which means they're currently out of phase. So we're going to have to get them back into phase by using m plus 1/2. Let's go to the next slide to see this in action. All right, we want maximum reflection, so therefore we want constructive interference, which means in order to get those waves back into phase, we're going to have to use m plus 1/2 in here. First, you convert the wavelength to figure out what the wavelength of the light in the film is. So because the light is traveling slower, so remember lambda equals v over f, because the light is traveling slower but the frequency stays the same, the wavelength will decrease. We can use our equation, combine these equations because the frequency stays the same in order to find the new wavelength. All right, because we have m plus 1/2 in here, we want m to be the smallest possible value without the entire equation going away. We can actually make m 0 here because we have this 1/2 in here. So we see that the minimum thickness is 138 nanometers.